This image is contained in the K-10 NESA mathematics syllabus, and according to the document, illustrates the central role of working mathematically in mathematics K-10 teaching and learning. While the syllabus document acknowledges that communicating, problem-solving, reasoning, understanding, and fluency are all interrelated components that allow an individual to work mathematically, I believe that this visual does not necessarily succeed in demonstrating the interrelatedness of these skills. For one thing, the vertical nature of the components could be interpreted as representing an individual list that one needs to tick off, sort of like a shopping list. This is especially true, as Bobis et al. Explains, maths has traditionally been thought of in terms of content, a body of facts and procedures that needs to be memorized. My image is clearly not made by a graphic designer, but to rectify this, my image has all 5 proficiencies represented horizontally as roots, which support the overall goal of working mathematically, represented by the tree as a whole. After feeding Bragg and Herbert, I wanted 4 roots here to lead to reasoning. Here, as reasoning is described as the glue that holds everything together. One uses it to navigate the many facts, procedures, concepts, and solution methods to see that they all fit together in some way. However, after reading Bobis et al., I realized that the same could be said about problem solving. As they write, all proficiency strands are intrinsically linked to an overarching process, the process of problem solving. I ultimately decided that the best bet would be to draw attention to the interrelatedness of these proficiency strands rather than emphasizing some over others. In this way, my image mirrors that presented by Peter Sullivan in his shape paper, which established the principles of the Australian curriculum mathematics. Finally, I wanted the things going around the tree to represent the 3 strands of the mathematics curriculum. For statistics and probability, I have 4 birds with sexes that go from male to female, and finally a question mark. The question is deliberately vague and takes inspiration from the work of Sullivan and Mulligan, who note that a good question may have several acceptable answers. In this case, a student might look at the 4th bird and ask if the sex of the birds follows a pattern, thus being a female, or if the sex of the bird is dependent on probability, thus it would be 50-50 odds of being either sex. For number in algebra, we have a child in the tree asking how many apples should I take. The open-endedness of this allows for various levels of mathematical reasoning to be applied. One child might look at how many apples are in the tree and think, well, we should take all the apples, while others will think about how many could fit in the bucket you see over here, and another will think about how many one child could take, etc. Finally, for measurement and geometry, I have a child next to the tree asking, is it true that this tree is bigger than that tree, while pointing to this tree in the background? The goal of is it true questions is to prompt mathematical reasoning through encouraging children to justify their stance. In this case, there is no obvious correct answer. Instead, students are being prompted to ask questions such as, how far away is the tree? What does the person mean by, is this tree bigger? Are they simply referring to the height, or are they referring to its mass as well?